Okay, good morning, everyone. Today, Leonardo will tell us about Cotangent Schubert Calculus.
Thank you very much. Thank you for the invitation. It's an honor to be here and to speak at the seminar. So I have a 2-hour talk, and when I started preparing, I realized that 2 hours is more than 1 hour, but it's much less than 3. So I'll do what I can. I'll tell you essentially my goal for today is to introduce this object. It's not an object, but it's an area called Cotangent Schubert Calculus. So we started to study this maybe a few years back, and now we have more and more results. So I'll tell you about the basics of this, but I will probably not be able to cover all the applications that we have at this moment. So first of all, let me just tell you about the Schubert calculus. And in order to tell you about that, I'll tell you what are the main objects in this talk. So first of all, maybe I should say that the work that I did is in collaboration with many people here that are mentioned. So I'm going to mention some of these names, maybe not all of them today. Okay. So let's talk about flag manifolds. So X for me is going to be a flag manifold. And if you want to kind of put a name to it, of course, maybe in this seminar, I shouldn't define what a flag manifold is, but just in case, FLN is going to be the sequence of complete flags in Cn. So everything is going to be over C, although some of this can be generalized over fields of characteristic 0 later on. And then I want to regard this flag manifold as a homogeneous space for the in this case, let's say for SLN. So it's going to be written as SLN modulo Borel group, where, for example, you can take the Borel group to be the group of upper triangular matrices. The Grassmannian is, again, a homogeneous space for SLN, where you divide now by a maximal parabolic group, which can be seen, for example, as this is the subgroup given by these matrices, where they have like a 0 on some top left corner. But most generally, the story that I'm going to tell you today works for this G mod P, where G is a complex semi-simple Lie group and P is a parabolic subgroup. Of course, the more you specialize, the better the results are, just because in this generality it's much harder to work. Okay, so and if we work in this G mod P generality, then I'm going to have a maximal torus, which you can think of as just the torus of diagonal matrices obtained by intersecting upper triangular with lower triangular matrices. So this is the opposite Borel. And this torus is included in this Borel subgroup, which is included in some parabolic group, which we fix, and in the group G. Okay, so in this talk, we're going to discuss about various things about this diagram. So this is a diagram of cohomology rings, where each of these cohomology, generalized cohomology rings, where each of these cohomology rings is associated to one of these homogeneous spaces. So X is the G mod P. Now I consider here 4 rings. In my double life, I also like to study the same diagram, but where I put Q everywhere here. So there is in fact a cube here with everything can be cubed, like quantum everything. So this is the usual cohomology. This is the equivariant cohomology. This is going to be K theory, and this is going to be the equivariant K theory. I will not go on, and I will not define what the equivariant cohomology and equivariant K theory are. If you know what they are, it's great. If you don't, I will not. I'll just say that whatever I'm talking about is going to work in the equivariant context. So there are various relations between these rings. For example, the cohomology rings, the usual cohomology and ordinary cohomology and equivariant cohomology, these are graded rings. So there is a grading that we can put. You go from the equivariant to the non-equivariant ring by making certain equivariant parameters equal to 0. The K-theory rings are not graded, they are filtered rings. And then we can recover the usual cohomology ring by taking an associated gradient with respect to that filtration. There is something called topological filtration. You can take the associated gradient, you're going to get that. And so you go from the K-theory to cohomology, or equivariant K-theory to equivariant cohomology. Again, if you work equivariantly in K-theory, then you have to make the calculus. Ti goes to 0, now it needs to be exponentiated. So e to the ti goes to e to the 0, which is equal to 1. So whatever I'm saying works equivariantly. If you want to consider non-equivariant statements, then you'll have to make these specializations. Okay. All these rings, they are equipped, as I said, they are homogeneous spaces. They are homogeneous spaces for G. Now this, if you fix a Borel subgroup, if we fix, let's say, upper triangular matrices, then they also have Borel orbits. And in fact, they have finally many Borel orbits, and these finally many Borel orbits are called Schubert cells. Everybody knows this, I guess, in this room. So this is my notation. I'm mainly introducing this for the sake of notation. So the Schubert cells for B will be denoted by X lower W, and the Schubert cells for the B minus, for the opposite Borel, they're gonna be denoted by X upper W. Why am I doing this? Well, I'm doing this because if you do intersection theory, it's good to intersect cohomology classes, and for those the codimensions add up. But the theories I'm going to talk about a bit later on are going to be mostly homology theory. So for those, the dimension is good. So the X uppers, they are indexed in such a way that I record, so the cohomology class for the closure of this Schubert cell, which is the Schubert variety, is going to be in complex degree length of W, but the homology class of the Schubert variety X lower W is going to be in the homology complex degree length of W, okay? So this is just a notation to keep in mind that whenever I put lower, it's like a homology thing. Whenever I put upper, it's like a cohomology thing, and indices add up. All right.
When you write this down, you're thinking of the flag variety right now, right?
Yeah, so I was writing here things for the flag variety. Otherwise, I have to introduce all these subgroups of the Wall group, which will give you representatives for the Schubert classes in the G mod P. So you have to pick, your parabolic. To choose a parabolic means to choose certain simple reflections or maybe nodes in the Dynkin diagram. And these simple reflections will generate a Wall group, which is a subgroup of the full Wall group. And then you take quotients by that. And then you take minimal length representatives, and those will index the Schubert classes in G mod P. So for example, if you work in the Grassmannian, it's not going to be exactly that. It's going to be, the Schubert classes are indexed by partitions, and those correspond to minimal length representatives in a quotient. So that's okay. So the Schubert cells, Schubert varieties are just closures of Schubert cells, and the Schubert cells give me a paving by affines. In fact, a stratification of the flag variety. And we're going to use this geometry to construct something that I like to call the Schubert package. And this Schubert package is going to be, so I'm gonna say what I consider to be the Schubert package for G mod P, and I'm going to try to fill this table as we go along in the talk. So what will be the Schubert package for G mod P? So far, what do we have? So we have a bunch of generalized cohomology theories with a pairing. So we have a ring plus a pairing. The pairing that we consider is just the usual intersection pairing. In cohomology, it's just you multiply two classes. It's the same thing in K-theory. In K-theory, it has to do, of course, with the holomorphic Euler characteristic. In cohomology, it has to do with taking degrees. So what is the Schubert package? Well, the Schubert package consists of, so now I have a ring with a pairing, and I need to fix a basis. So what is the basis that I want? Well, so I'm going to take the cohomology ring of X. Let's say X is G mod B, or the flag variety. And because G mod B, and in fact all the G mod P's have a stratification by Schubert cells, this implies that the closures of the Schubert cells give you a basis for cohomology. So I'm gonna take it in this way, and it's also this way. In fact, I have two types of bases. So these are the fundamental classes of the Schubert variety. So far I have a ring with a basis. In fact, I have a couple of bases. What is the second thing? Well, we need a duality. So this is a ring with a pairing. Once I give you a basis, you're going to ask me, what's the dual basis? It's kind of like foundational to the theory. So what is the dual basis for the Schubert basis? Well, the dual basis is here. So the dual basis for the Schubert classes are again Schubert classes, but I like to write this upper and lower because really what this pairing is doing is multiplying these two classes together and is taking the degree 0 part. when you multiply these classes together, you get something called the Richardson variety. And that Richardson variety has dimension 0 exactly when u is equal to v. And in fact, it consists exactly of a point. So that is telling us that in some sense, the Schubert classes are self-dual, because this is in fact equal to this, where W0 is the longest element in the var group. And so in fact, this is just a relabeling of the other bases. Okay. All right. Okay. So maybe we want to talk about positivity. Let's write it here. So positivity. So what is positivity saying? So it's saying that, okay, let's say that you want to multiply two Schubert classes together. So now I want to get these versions which are good for cohomology calculations. So you get some coefficients. The coefficients are integers. And then you start to calculate the coefficients. We know how to calculate the coefficients in abstract. They are just the pairing of the multiplication of two Schubert classes with the Poincaré dual, with the dual of the third class. So the dual of the third class is x lower down. So when you calculate this thing, you can use the Kleinman-Bertini theorem. And I should be careful when I say when you calculate this thing, because you're not really calculating. This is more like a theoretical result. So you use the Kleinman-Bertini theorem, and you're going to find out that this is the same thing as the number of points in the intersection of three Schubert varieties coming from these cycles in general position. Maybe this is familiar to everyone. In particular, this is a non-negative integer. So that's what I mean by positivity. So in the Schubert package, we're going to have a basis, we're going to have some dual basis, and then you want to multiply elements in the appropriate basis in such a way that the structure constants have to be positive. There is no reason that this positivity is going to hold, but in all the Schubert theories that I studied, positivity comes up. Somehow, if you have a good, that's my philosophy, that if you have a good cohomology theory to study for flag manifolds, then it must exhibit some positivity. And that's what I mean by it. Okay, so far this is more theoretical, but of course the big question is, how do we actually calculate such things? And this would be the fourth part of the Schubert package, which in some sense is the larger one. So the algorithmic part. So the question is, how do you calculate such things? And because these are actually counting something, you want to calculate them in a manifestly positive way, right? So you want to say that the Schubert structure constants are actually counting some sets, which can be defined in a combinatorial way. Okay, so there are many algorithms, but from the point of view of this talk, I'll just say the following thing. So usually, so let's say that you look at H star of G mod B. Now, this is going to be, in fact, a quotient of, let me even put FLN here. I can do this for any G mod B, but let's put FLN. So this is going to be a quotient of some polynomial ring. Okay, so there's going to be something like this here. And the question is the following. So one approach, one strategy to calculate these things, so there are many strategies, but one strategy to calculate these things is to somehow replace the calculation that happens in geometry to some type of calculation that happens in a polynomial ring. But in order to do this, you have to be able to actually see what polynomials correspond to Schubert classes. And how do you get such polynomials? There must be some type of guiding principle that tells you what polynomials to pick. And then one guiding principle is to use these divided difference operators. It tells you that whatever polynomials you pick, they have to satisfy something called a divided difference equation. So they can be defined in the following way. So let's say you work with FLN. And here I'm going to forget the ith component, right? So this is a flag and this is the same flag, but where the ith component is forgotten, right? So this is a P1 bundle here. So this is again FLN. And I think I call this pi I over there. I hope I did, yes. Okay, so I'm going to define an operator here, which is going to be just the operator given by push-pull. So pi I upper star of pi I lower star. Okay, so this is some operator in here. So you start from here, you start with some class from here, and then you push forward and then one can prove. So it's actually not difficult at all to prove that the following holds. If you apply this operator to a Schubert class, then you either get the next Schubert class or you get 0. So here I'm giving the version for so this type of operators really exists for a G mod B. So for a theory, it's a G mod B theory, it's the full flag theory. So here I'm indexing things by codimensions. I want my codimension to decrease. So I want WSI to be less than W, and this is 0 otherwise. So let's look at this equation. So what is this equation saying? So this equation is telling you that if you start from the point, you get to the Schubert variety which has dimension 1. If you start from something with dimension 1, you get to something with dimension 2. So in other words, if you know something about the point, you can generate the full theory starting by just applying these operators over and over from the point. It turns out that these operators, and this is why I started to fill up this table here. So this is the table about the Schubert package. So the basis that we're considering here is this XW. So these operators here satisfy very nice relations. So for example, you can already check from that formula that if you take the square of that, you get 0. You can also check that these operators satisfy the Brady relations. In particular, you can define such an operator for any Val group element. So you can say, for example, using these operators that x upper W, it's gonna be something like this. So probably I'm missing a W0, but yeah, I think the W0 should be W. Let me just write it. So it's gonna be W0, and this is gonna be W. Maybe it's gonna be like cycle 1. I could be off by some of this. But the point is that this is the class of a point, and then you can define a divide difference operator by any for any Val group element, and you can get all the other classes just by applying to the class of the point. How does this help? Again, the picture that we're trying to construct here is somehow trying to relate this to some algebra, to some algebraic object. Yes?
Is this a type A thing, or do the pi maps exist in other things?
Yes, the pi maps exist in other types. So what you have to do is you have to take the minimal parabolic corresponding to a simpler reflection. So this would be, yeah, so this G mod Pi would be exactly this flag manifold. This is again a P1 bundle and so on. So this is very general. So it turns out that some operators like this also exist on the algebraic side, and these are divide difference operators that are defined in the following way. So if you want to apply some operator like this to a polynomial, you get something like so maybe P, and this is x1 dot dot dot, and this is xi plus 1 xi. So you have to exchange the coordinates for xi plus 1 and xi, and then you have to. So this map is going to be consistent with these operators, and this actually, and then what you need to understand is what is a good representative for the class of a point. Right? If you know what is a good representative for the class of a point, and then you understand everything else. And it turns out that Lascaux and Schützenberger, they had a very good monomial, a very good representative for the class of a point, that this is the theory of Schubert polynomials. Okay, so I'm not getting into the Schubert polynomials, I just gave a glimpse of what could be possible. So this is the goal of this board is somehow to tell you that one possible way to get a hold of these coefficients, these Schubert structure constants, is to use these Hecke operators. And that should be the thing I'm trying to convey here, is that there are these Hecke operators all the time. And there is a particular degeneration of the Hecke algebra. I think in this case it's called the Mihalcea algebra, which actually governs the theory. So that's my goal. And then if you use that, then you can construct the theory of Schubert polynomials.
I understand why respecting grade relations is good, and I understand why starting from just one initial condition and then being able to propagate is good. I don't understand why they always look like divided differences.
Yeah, it's just so they satisfy, of course, the same relations. I think the only I don't know a good way to. So what you want an explanation of why this is true in relation to that. And
Or just like other things that also satisfy the
Yeah.
grade relations don't sort of come up for us.
so maybe Andy has something to say.
It's localization along the P1. It's equivariant localization along the P1, and so that's why the denominator shows up and then so.
So actually we were thinking exactly the same thing. So I wanted to say localization, but then if we get into localization, then of course, yes.
I'm happy with that. Thank you.
How about that monomial? Is it easy to say that why that monomial is the right monomial to choose?
It's not easy to say. In fact, if you look in the this divide difference operators, they came up in a paper in '77, I think. They are called the BGG operator in cohomology. So it's Bernstein, Gelfand, and Gelfand. And already, if you look in their paper, there is a particular class. They don't work at the level. They write a presentation like this. You have to put Q if you work in GMAT. So they write a presentation, very general presentation, this Borel presentation of the flag variety, and actually they give a representative for the class of a point. It's very different from Lasquin-Schutzenberger. It's something that actually, if I remember right, it involves division by the order of the var group. So you're dividing by n factorial. And it's something that you can check, that it represents the class of a point, but it's not good for combinatorics. This particular monomial that you get so the Schubert polynomial has beautiful properties. For example, it has a monomial expansion with positive coefficients. The coefficients can be seen, for example, using the geometric vertex decomposition, I think, that Patricia talked about yesterday. So you can actually see those monomial coming up from the generations of some matrix Schubert variety. So yeah.
Why is it called Hecke operators? Normally I know Hecke algebra.
Yes. So there is a Hecke algebra. So Hecke algebras come up in many contexts. In particular, I don't know if it's the first time or not, but they come up in number theory. So these particular relations. So what I'm focusing on is on these relations. These particular relations are the relations that are known to hold in all the contexts where these Hecke algebras come up. So the Hecke algebra is an algebra, so there are various versions of it, but it's an algebra which is generated by things like this and satisfy things like this. So they are generated by I, a simple root, where the relations are this. So this is not the full Hecke algebra. The full Hecke algebra is actually here. And you should think of this Y, so it comes up in number theory. This Y has to do with the number of points in the residue field. So the Y is the Q, the number of points in FQ. So this is, other terminology, this is just because of these relations. These relations are always associated to objects which are called Hecke objects. And the Hecke algebra in geometry and the one in number theory, they will meet. I don't know if they meet in this talk, but they certainly meet in the continuation of this talk. So, yes.
I was just gonna say, I think that one of the reasons why the representative, like the Lesko-Schutzenberger representative is so good is because it has least possible degree of all the representatives that you could choose in the domain of that projection there.
Well, they all have the same degree. I mean,
No, because there's stuff in the kernel that you can add anything.
Yeah.
but there's other representatives of the same degree, though.
That's pretty
So I think if you take the product of the positive roots and divide by W.
That's right. You take the product of positive, that's the BGG formula. Schubert polynomials are really good if you look at stability, for example. You can actually determine them uniquely by some stability property. So there is, if you work in FLN, you can imagine that in fact this FLN doesn't come alone, comes with all its family, which is FLN plus 1, FLN plus 2, and so on. And then you work in FL infinity, so you have a sequence of varieties, and then you have maps backwards in cohomology. And then all these operators exist there, and then the Schubert polynomials that you can define, they satisfy some stability. So when you pull back a Schubert polynomial from like a higher flag manifold, then you either get 0 or exactly the same thing. And I think there is a theorem that says that actually characterizes the Schubert polynomials together with some. So this stability essentially characterizes. I'll try to say something vague enough that could be true. So the stability property characterizes the Schubert polynomials. If you go to the double Schubert polynomials, you have two types of difference operators, and then there are results of Fomin and
Parallel?
no, okay, so it's Fomin and somebody else in type A, and then there is the Billy-Hyman polynomials in other types. You have to be a bit more careful. Those are not polynomials; those are power series, but they are still characterized by some stability properties. Then you can continue with that and define polynomials in other types as well. Yes.
I'm just
Yeah.
like behind everybody else. Could you explain the surjection a little more concretely?
I don't want to. Okay.
Xi goes.
Yeah. So I can go like this. Xi goes to the first Chern class of Fi over Fi minus 1. Oh, like this. So you on the flag manifold, you have a tautological sequence. Right, there is a tautological sequence of bundles, and then you can send Xi to, so this would be Fn, can send Xi to the first Chern class of the portions of this one. So these are the Xi's, and in fact these are the same that come up in. You can also have like a more fancy way with fundamental weights and so on. So if you want like a full G-mod B generality, then you want to probably put less than n. You want to put the number of simple roots there. I can explain why they generate and so on, but maybe. But these are, so geometrically, this is what they correspond.
This is the presentation where the kernel is the W invariant.
Exactly. This is the presentation. Thank you. So this is the presentation where the kernel. So maybe I'll say it this way. Where I goes from 1 to n. Okay, so the kernel is given by the elementary symmetric functions in the variables. How do you really see this? Well, you see this from the Whitney relations here, because the ith elementary symmetric functions in these variables is the ith Chern class of Cn. Cn is a trivial bundle, so the ith Chern class is equal to 0. You can even upgrade this equivariantly, and then the ith Chern class of Cn equivariantly, it's again an elementary symmetric functions in the equivariant parameters. And then you get the equivariant version of this. Okay. All good with the Schubert package. Very good. Let's go to cotangent Schubert package. Oh yeah. So for the sake of time, I didn't tell you. Maybe I'll indicate very briefly. I drew a diagram here, so it sounds like you believe me that exists a Schubert package for this. Maybe you also believe me that exists a Schubert package for this. In fact, I wrote the basis in such a way that everything is actually good equivariantly, except for this part. You cannot have now a positive number. You have a different type of positivity, and in fact, Bill Graham actually proved the positivity in the equivariant context. How about K-theory? So what is the Schubert package in K-theory? So in K-theory, you have a different basis. Again, instead of considering fundamental classes in K-theory, you're going to consider these classes of structure shifts of the Schubert varieties, so you get something like this. So, so here OW is just the class in K-theory corresponding to the coherent shift supporting the Schubert variety XW. So that is the basis. What is the duality in K-theory? So you have something like this. So the dual of a Schubert class is something called an ideal sheaf. So this ideal sheaf is the class which is given by, you take the structure sheaf of the Schubert variety, xv, but you have inside that you have a Weil divisor, so which is given by the boundary of that. So it's the union of all Schubert varieties corresponding to Weil group elements which are 1 less than b. Okay, so this is some class here. So for example, if you start with in Pn, then this will be O of -1s. Okay, in Pn, and so this is the Schubert package. And then in K theory, if you multiply two such things together, you will get different type of coefficients. So let's call them, I don't know, let's call them B, maybe not, DUVW. So what would be these coefficients? So these are just some Euler characteristics now. And there is no reason for these Euler characteristics to have positivity. But if you believe what I said at the beginning, everything should have positivity, otherwise it's not a Schubert law. So this has positivity, so it turns out that -1 to the, so this is the K-theoretic positivity. This is a theorem that for Grassmannians was proved by Anders Buch, and then in a combinatorial way, and then Brion actually gave a proof for any G mod P. You can actually, it's actually fun to see this for Pn. Maybe I'll indicate in a corner, as usual, the proof. I could write the full proof, but I don't have space. So, so you can kind of see this positivity happening, for example, in the K theory of Pn. So let's say that you want to multiply two Schubert classes. The Schubert classes in Pn are just smaller projective spaces, right? So then you have some type of coefficients here. I don't know. So these are. So now I have D, A, B, C. It's great notation. So this is OP to the C. So okay. So here, when you multiply two structure sheaves, in fact, this is a structure sheaf of a linear space. It's OL, where L is just the intersection of the two linear spaces. This is something about the fact that you can translate things in general position. And then when you translate things in general position, OX times OY, it's OX intersected to Y. Okay. So then you calculate this coefficient. So you have to essentially expand the class of a linear space. Maybe, I don't know, maybe some coefficient here and CA times OPA. Okay. So then what would be this CA? Well, I told you that, let me erase the Kleiman-Bertini. So I told you that this CA, it's the Euler characteristic of OL with the dual of this OPA, but I told you that the duals in projective spaces are just O of -1s. So what you really have here is O of Pn minus A of -1. Okay, that's what that thing is. Well, this is just O of, there is a new L prime, which is just the intersection of this linear space with this Pn -1, right? That's what this thing is. And now you're looking at the other characteristic of O of -1 on the projective space. That other characteristic, so the cohomology groups are 0, except on the very top. And that's where the sign is coming from. So the only non-zero Euler characteristic is coming from the top. So this is just the -1 to the appropriate thing. And then this is the dimension of H dot of this minus. Okay. So that's why there is a sign. If you follow this idea, actually you will stumble onto the positivity for K theory, and it's much more complicated. So this is a consequence of Kodaira vanishing in this case. But if you want to do this for any G mod P, then you have to use a different vanishing theorem, which is called Kawamata theorem. And this is what Brion said. So Bion essentially applies Kazhdan-Lusztig to prove that in the calculation of the structure constants, of the coefficients that he wants to calculate, only the top cohomology may exist, and that one has the correct sign.
This is a characteristic zero result.
This is a characteristic zero result. I think so. Yes, I mean, Kodaira vanish. Yeah, you have to worry about things.
But the structure constants are independent of the characteristic.
This is okay. So the proof I'm discussing about Kodaira vanishing, about Kawamata-Vivek. I think you need conditions in characteristic P, like Frobenius split or some other things for those things to hold. Yeah.
Well, I think you could calculate the structure constants maybe in the same way.
Yes. This is
in the
Matt is
form
saying.
that might be, that's what Matt's saying.
Yeah. So this is what Matt is saying. So I'll just say that okay. So if that's true, then it's all fine. But maybe the proof may not extend. Yeah.
I just had a naive question. What's the relation between the C's and the D's? Or there's no.
Very good question. Thank you. So as I said, the cohomology is not, K-theory is not graded. Cohomology is graded, K-theory is not graded. So in cohomology, these structure constants are non-zero only if this condition happens. Length of U plus length of V is equal to length of W. In K-theory, you only have that condition happening. So, wait. Yes, I think that's right. I think that's not right. That's right. Yes. So in K-theory, only that condition happens. So the two are the same exactly when the equality holds. In general, K-theory has more things. The simplest example is when you go to GR24, for example. In GR24, if you take divisor times divisor, like this, you get the usual thing minus this thing, right? So this is these are the usual classes in cohomology, and this is the extra class in K-theory. Okay.
So in characteristic P, we know the sign of the Euler characteristic, but probably we don't know that all the cohomology groups are zero except.
Yeah. That's what I was. That's what I'm getting. Yes. Is this okay, Alan? Yeah. So they are the same in. I mean, this is consistent with the fact that the associated gradient of the K-theory is equal to cohomology. So that means you have to recover the cohomology structure constants when you have the correct degree. Okay, so I think I'm done with page 1. Oh no, also with page 2. So okay. All right, so let's talk about cotangent. But it's great. So please ask questions. I'll do as much as I can. So I'm not going to worry about as much as we cover. You know, I'm here the next semester, so I'm willing to ask any questions. To answer any questions, I can also ask. Yes. Okay. So all right. So in K-theory, maybe I should mention, since I talked about K-theory a little bit. So there is also positivity here. The basis that we took was this basis. The basis consisting of structure shifts of the Schubert varieties. And then this basis was well behaved with respect to these Hecke operators. The Hecke operators were defined exactly in the same way. Push-pull operators. There was no difference. The only difference is that now this push forward and the pull backs are actually happening in K-theory. So you might have higher direct images, things like this. You don't, but that's a theorem. And then, so now you get a slightly less degenerate theory called the Nil-Hecke. It's a Nil-Hecke algebra where the operators satisfy the Brady relations, and this is the telltale relation for the Hecke for this Nil-Hecke is that delta I squared is equal to delta. So of course you can see I'm kind of hinting here. There are two more degenerations we're going to consider. In fact, this is not a degeneration anymore. This is the full Hecke algebra. So, what's the hierarchy here? So what are we considering? What are the bases that are well behaved with respect to this basis? So this comes from the theory of characteristic classes of singular varieties. Okay. So maybe I'll define that. And I will have to tell you how is that related to anything cotangent. I call it cotangent Schubert calculus, but there is nothing cotangent so far. Okay, so this has to do with this theory of characteristic classes. So I'm gonna change gears here, and then let's say that X is some algebraic variety over C. And then I'm going to define something called f of x, which is the group of constructible functions. So this is so the elements of this group are just integer combinations of indicator functions of V, where this is a finite sum, and Z inside X is constructible. Okay, so this is called the group of constructible functions. You can obviously add such objects, constructible functions. There's a push forward here, so if you have a proper map from X to Y, then there is this is proper. Then there is a push forward from f of x to f of y. It's enough to define this push forward on indicator functions. So 1z. So f lower star of 1z. Well, this has to be a constructible function on y. So if I evaluate it at the point of y, this is going to be the other characteristic of the preimage intersected to y. So now I have to be careful. Normally I should put here other characteristic with compact support, and this would be true. But over C, the compact support and non-compact support are the same. In general, you want to put compact support. So, all right. So this is now a theorem. This is MacPherson 1974. And this was a conjecture, in fact, by Delining-Grothendieck earlier. It says the following. There exists a unique transformation, C star, which goes from constructible functions to homology. So this is a homology theory, such that two conditions are satisfied. So one, if X is smooth, then C star of 1x is just the total Chern class of the tangent bundle of X, but this is a cohomology class, so you have to homologize it. So you have to capture the fundamental class. And then this transformation is natural. So C star commutes with proper push forwards. Computes with proper push forward. So in other words, you have a diagram. With C star, this is. So this is nowadays called MacPherson transformation, and the hard part of this is the existence. The hard part of proving such a thing. It's easy to see, for example, using blowups. You can always reduce it to something smooth, but you have to worry about this thing being modified. Okay. So if you use this, then by definition, if you have Z inside X constructible, then C star, CSM, the Chern-Schwartz-MacPherson class of Z is by definition just the image of 1Z. So it's called, as I said, it's called Chern-Schwartz-MacPherson class. So why Chern, why Schwartz, why MacPherson? Well, Chern because this has to do with Chern classes for the variety X. In some sense, this class is a replacement for the class of the tangent bundle in case the variety may not be smooth. Okay. Why Schwartz? Well, it turns out, so MacPherson proved his theorem in 1974. The way he proved it, he used actually transcendental methods. So his proof is not in complex geometry, it's in analytic geometry. And it turns out, so he used a particular constructible function called the local Euler abstraction. So that was, it's an invariant of singularities that can be used to construct this transformation. And then it turns out that that particular transformation, in fact, up to some duality is the same as some transformation, some invariant of singularities that was defined a few years earlier by Mihalcea and Schwartz. But the actual fact was realized only 10 years after. So in 1982, maybe, it was proved that in fact the invariant that Mihalcea and Schwartz defined and the invariant that MacPherson defined were the same. Okay, so all right. There is nothing cotangent about this, right? What is the cotangent? Maybe I hinted that there is something here. Let's see, yeah. So what is the cotangent? So what's going on here? So what we're really trying to define, or what is defined by this theorem is this class. This is a class in homology. You can imagine that this x, at this moment, I'm taking x to be just an algebraic variety, but for the cotangent thing, I have to embed x in the manifold.
Did you say whether this construction uses resolution singularities?
The construction does, as far as I know, does not use resolution of singularities. Yes. No. It's a different construction. So by now, there are some other ways which are coming from this direction to redefine everything. So from now on, I'm going to assume that x is smooth, and I'm going to be interested in the CSM class of some z inside some x smooth. So in this case, this transformation is actually related to something coming from the cotangent bundle. More precisely, this C star, so you take the cotangent, so x is smooth, right? So you have the cotangent bundle. And then the cotangent bundle has an extra C star action on the fibers. I'm going to put the action with this character minus h of h inverse as a multiplicative notation, okay? So it turns out that that C star, so maybe I should just write down the formula. Maybe that's the easiest thing to say.
We need resolution to deduce uniqueness.
Yeah, I guess Andy asked if the construction is, yeah, you can, the uniqueness follows from resolution of singularities, yes. So it's, but about the construction does not use resolution of singularities.
So uniqueness is not just some form that contains these two properties.
But existence relies on the existence of the solution.
So once it exists,
Uniqueness.
once it exists, resolution of singularity to show it's unique, because you reduce to things which are smooth.
Wait, but here in one you just need x smooth, or you need some more assumption?
No, here there is no assumption here.
But
here
for the formula for
x is
one,
smooth.
no, but I mean, to use this, can I just partition? Do I have to resolve singularities? Can I just
If x is smooth and compact.
compact? Okay.
I will probably disagree with the compactness. It's true as stated. So but compactness is good. So you need some properness if you want to relate this to the other characteristic. I think you don't. So MacPherson puts compactness as part of the definition. I think later on you can drop it. You can just say this. You still need proper maps here. So you can work with non-compact varieties, but you'll need proper maps to relate.
And there will be no problem with capping and so on.
Yeah. Okay. So yeah, you have to work in a theory, right? Okay. So you have to work in a theory where this is defined, right? So the fundamental class is defined. So maybe you want to work in some Borel-Moore homology, things like this, or maybe you want to work in Chern.
Because my question was, couldn't we like replace resolution of singularities by somehow partitioning X into like smooth locus and the rest?
You can partition X in the smooth locus, but the problem is that the fundamental classes that you're going to define will not behave well with respect to the global fundamental class. So that will not really give you a, like for example, you can partition P1 into a cell and a point. Now, a cell has trivial, so if you do that, then you will not get anything, right? Because the cell is contractible and the point is contractible, so the total Chern class of everything is actually.
So we need something more than smooth.
Well, I mean, it's the theory will not tell you much if you do that. If you apply this theory for a cell, it's true as stated, but it will not tell you much. For applications.
I see.
Yeah.
But you're gonna apply this to non-compact Z's, I guess.
Yes. That's exactly the point. I'm gonna apply this for constructible Z's inside X, which is compact. Yes, indeed. Yes. Can I take 2 minutes to just wave my hands here a little bit? This is the fun. If I wave my hands fast enough, then you can ask me in the break. So I'm claiming here that the theory that is defined there is actually related to some theory that is coming from cotangent bundle, and this idea actually comes from Saba and Ginsburg, 85-86. Botong also mentioned this. So the idea is that the theory. So this is what Saba said, in fact. So the theory of Chern classes of X, and this is what he means, is equivalent to the Chow theory of the cotangent bundle, in the sense that the Chow theory of the cotangent bundle only involves fundamental classes of objects coming in the cotangent bundle. And you can see it in this formula. I'll just say something like this. Right. So I'll say if you're interested in the value of MacPherson transformation for some constructible function in f of x, that's the same thing as, well, you have the cotangent bundle, you have this extraction here, you have some object which I'm going to talk about in a moment, called the characteristic cycle of this constructible function. So you have to pull back this cycle here in a C-star equivariant way. That is the statement. Now, if you believe in this statement, and this statement will tell you that indeed the theory of Chern classes here is equivalent to something coming from fundamental classes on the cotangent bundle, because this is something on the cotangent bundle, and this I upper star, in fact, it's an isomorphism. Okay, so you have to be a little bit careful. So what is this characteristic cycle? So this characteristic cycle, in fact, is a Lagrangian cycle inside the cotangent bundle. So this is this part of the picture here. So the characteristic cycle is a Lagrangian cycle. So that means, okay, the symplectic, the cotangent bundle is a symplectic variety. There is a notion of Lagrangian cycles in there. They are middle dimensional and they are Lagrangian with respect to the symplectic form. And then you can form a group called the group of conic Lagrangian cycles. Conic means that they are stable with respect to this dilation. And then you have this pullback via the zero section. So the pullback via the zero section is what is giving you this C-star of u. Now, that formula reflects this corner of the diagram, but the diagram is much bigger. This is a diagram that arises in the of Kazhdan-Lusztig conjectures. So it's a diagram that relates several objects. So on the bottom, you have this characteristic cycle map, which is an isomorphism, in fact, between constructible functions and these conic Lagrangian cycles. Is defined in the following way. So it's determined by taking the conormal cycle of a variety. So X is smooth, Z is irreducible here. This conormal cycle is by definition the closure of the conormal bundle of the regular locus, right? So Z may be singular, this may not be defined. But what you do is you take the regular part that is a bundle over the regular part, and then you can close that thing up inside T star of X, and this is called the conormal cycle. So this is this conormal cycle. You want to take its class in the C-star equivariant way, and then this corresponds to up to a sign to this this function that I described before called local Euler abstraction, which I will not define. I'll just tell you that this is a function that was defined by MacPherson. It's a very interesting function, and essentially, knowing this function is equivalent to knowing these guys here. These guys happen to be exactly the irreducible conormal cycle. So every element in this conic Lagrangian cycles, it's a combination of such things. And such a conic Lagrangian cycle is irreducible if and only if it's of this form. That's what I'm saying. And this is a theorem, was proved by Kashiwara proved it, Kennedy proved it, so there are several. Okay. On the upper side is where the Kazhdan-Lusztig theory lies. So here you have a regular harmonic dx modules, and here is the Riemann-Hilbert correspondence, and there is a de Rham factor that goes from the category of regular harmonic D modules to pervert sheaves over X. So these are some complexes, constructible complexes here. And these are dx modules, a regular harmonic. And there are two maps. So if you have a complex, you can take the stock Euler characteristic. By definition, this has to give you a constructible function. And here you have, if you have a regular harmonic D module, you can get something, you can define something called characteristic cycle in microlocal geometry. And the point is that this diagram commutes. I will stop here and I'll take the questions in the break. Sorry to go over that.
If you apply the MacPherson C star to the Euler abstraction, do you get the MacPherson Chern class? Is that what you're?
Thank you for the question. It's a very good question. So it's I have three favorite things I want to apply C star to. One of them is that if I apply C star to that, I get something called the mother class. This is the mother class, which can also be defined using the dash blow-up. I want to apply what I'm going to do is I'm going to apply the C star to the indicator function of the Schubert cell. Well, that one, in the proof of Kazhdan-Lusztig theory, there is something called the Verma module. So the Kazhdan-Lusztig theory has to do with finding out the transition matrix between the characters of two modules. One is a Verma module, and the other one is an irreducible quotient. The Verma module has a maximal module, and you have to take the quotient by that. So the Kazhdan-Lusztig theory is about writing the transition between the two. It turns out that if you take the dx module corresponding to the Verma module, and if you follow this, it's Bailyn, Simon, and Bernstein that prove that this is exactly the indicator function of the Schubert cell. I will explain this a bit after the break. Yeah, so there are three objects that I want to apply. One is the mother class, one is the CSM class of the Schubert cell, and the third one is the Kazhdan-Lusztig class, which is looming here because I have the IC sheaf. There is an IC sheaf here of Z, so that's if you do that transformation.
So C star applied to the Euler Z is the mother class.
Is the mother class. Yes, C star of the. So I will write that down. Yes. Thank you.
Will you take the indicator function of the cell and not the?
I will take the indicator function of the cell, yes, because I'm allowed, this theory is very flexible. So the theory allows me to consider images of things which are not closed, only constructible. And this, in some sense, the cell is kind of like the building block. Everything is built out of the cells. If you're interested of what happens with a variety, you're going to add up things that happen over the cells. So I will apply this to the cell, and magically this cell comes up in the Kazhdan-Lusztig theory. It corresponds to the Verma module. So it's kind of like one of the two things in Kazhdan-Lusztig theory. There is the Verma module and there is this irreducible quotient, which corresponds to the IC sheaf. So the Verma corresponds to the Schubert cell. IC sheaf, okay, corresponds to something that we define. It's called the Kazhdan-Lusztig class. Okay. And what Bill was asking is what corresponds to this one. This is going to be the mother. I will write the diagrams, but yeah.
Which module corresponds to the Euler obstruction?
Right. So I will not say, so the Euler obstruction corresponds to, I don't know what module corresponds to the Euler obstruction. what I'm telling you is that the Euler abstraction corresponds to the econormal cycle. So there are things, if something comes from here, I can trace it through the diagram and I will get some type of constructible function. So there is some module that corresponds to this, but I don't know what it is. We have two modules here, which are the Verma modules and the simple one. The Verma goes to the cell. The simple one goes to the IC constructible function. It's the one that measures the Euler characteristics of the stocks of the IC shear. Let's see if I can. Yeah, I'll draw a diagram maybe in the break. I should allow people to escape.